Okay, does my screen look good? Can we all see that okay?
Looks good to me.
Looks good? Okay, thank you. Caitlin, can you confirm that we're recording now?
Yes, we're recording.
Okay. I will be posting this on my personal YouTube channel. Those of you who follow me, I know there's a lot of people there that they're always bugging me for content, so I figured I couldn't let this go to waste. This is a rather timely presentation because we recently acquired a CS-corrected scanning transmission electron microscope here at the University of Florida. And the analogy, there's a few analogies that I like to use for this, but the one I put here on the title slide was it's like high definition TV for your STEM. Okay, so STEM again meaning scanning / transmission electron microscope. I will go over that term a little more in detail here. So you can see very clearly the before and after pictures, right? I mean, these are great if you're a company trying to sell a product, right? This is what my product can do for you. So you can see very clearly the definition in these images in the corrected version on the right. All right, let me make sure. Oops. Oh, there we go. Okay. All right. So just a little brief history here. I didn't want this to be too math heavy, so it isn't going to be, but we are going to talk about the origin of this term C sub S and what it means. So a brief overview of just magnetic lenses, because the lenses in your STEMs are magnetic lenses, or more appropriately called electromagnetic lenses, right? Because we know that the electric and magnetic forces are just relative versions of one another. But STEMs have many different lenses. There's kind of four main, well, there are four flavors basically: condenser, objective, intermediate, and projector. The most important one is without question the objective. And there's only one objective lens in any STEM that I've ever heard of. I've never heard of a system that has more than one. Most modern systems will have multiple instances of these other three types of lenses. And all of these lenses, they have defects associated with them. But in practice, the only one that really limits the performance of the microscope is the objective lens. Okay, so the biggest issue with magnetic lenses is just that the quality of them is just very, very poor in terms of what we're asking them to do. There's a very good so that would be simile. There we go. A very good simile in the Williams and Carter textbook on transmission electron microscopy, which is magnetic lens to use for microscopy is like using a Coke can as a telescope. Okay, so these are just not very high quality lenses. And when we talk about the problems with these lenses, what we're referring to are called aberrations, formally, that they're known as. Some of you may be familiar. I don't know how old some of you are. I mean, I certainly remember when they put the Hubble telescope into space, and they had a problem with aberrations of the lens on the Hubble telescope, right? And it was giving blurry images. So the main aberrations in these magnetic lenses, there's three of them. The most important one is the spherical one, and that's where we get the term C sub S, which we'll get to in a second here. I will discuss these other two, but that's what the C sub S refers to specifically, is spherical aberration. So your basic run-of-the-mill magnetic lens looks something like this. So it's got basically two parts. It's got over here these cone-shaped things, which are pole pieces. And then it's got surrounding it, these pole pieces fit inside this hole here, which is basically this cylinder that contains a bunch of coils of copper wire. And so you pass a current through that copper wire. And as we all know, when you pass a current through a wire, there's a magnetic field that is associated with that, and that magnetizes these pole pieces. And that's what generates the magnetic field that is used as the lens. Okay, so the actual part where the electrons go through is this little bitty part right here, just at the tip here. So this is only a couple millimeters, really. I don't know what the modern lenses are. This is actually a fairly dated image here, but you can see here, like, this is just how small this is in comparison to the rest of this. So this is your basic lens design. Okay, and so a great way to demonstrate this, I'm sure you've all kind of seen, this is kind of like a running internet gag, I think, the expectation versus reality, right? So your expectation with a lens is that you have something like this. Okay, so you have a lens here. In this case, it is a convex lens, okay? And you can think of each of these lines here as an electron that's coming through the lens. So what you expect to happen is all of the electrons come through and they get focused to the same point on the sample, okay? The reality, unfortunately, looks like this. Okay, so you can see that these electrons that are deviated from the center of the lens, which we call the optic axis, they get bent excessively and they don't end up getting focused where they should be. They get focused above the intended focal point, if you will. This is what spherical aberration is. There's another slide I'll show you about that specifically. So expectation versus reality. And this is unfortunately simply a result of the design of magnetic lenses. Otto Scherzer, who anybody who is very familiar with TEM knows and loves and holds up as like one of the heroes of TEM, he actually mathematically proved this just due to the inherent design of the lenses. Okay, so if we look at these aberrations of the magnetic lenses, we have one which is called chromatic. So that's basically a fancy way of saying that if my electrons have different wavelengths, they're not focused to the same point simply by virtue of the wavelengths being different. So this is not the most important issue, but it can still be relevant, particularly when the nominal voltage of our electrons goes down. If we move on from there, the next one we have is called astigmatism. This is the least important of any of these because we have hardware in our systems to correct this, which are called, appropriately enough, stigmators. Okay, so this isn't a big issue because we can easily correct this. But the most important one is spherical. Okay, and so this is, like I showed you in the diagram a minute ago, the idea that if the rays enter at high angles or distances from the optic axis, they're bent excessively upon exiting, so we can't focus all of those rays to one point. Okay, so this looks very similar to the diagram I just showed you. So instead of, but you're seeing, right, I have all these rays being emitted from one point here, and you can see they're entering the lens at different distances from the optic axis, which corresponds to, in this case, different angles as well. And you can see what I showed you previously, that these aren't focused to the same point. The ones that go out here at higher angles are focused too high, if you will. And then as we get closer in, they end up getting focused to where they should be. So we do see that there is kind of a compromise point here where you get a plane of least confusion. And if we don't have the advantage of CS correction, that's what we end up having to do, is we have to basically work with that plane of least confusion. So again, the rays that enter at large angles or distances from the optic axis are bent excessively. So this bending is proportional to the cube of this angle, which can also be related to the cube of the distance from the optic axis. I've simply shown it here as the cube of this angle beta. And this proportionality constant is C sub S. Okay, and that's where we get the spherical aberration coefficient, or C sub S in C sub S correction. This has units of millimeters. On most microscopes, depending on the quality of the lens, this can be anywhere in a non-corrected tool from maybe 0.5 millimeter to a couple millimeters. On our Talos TEM, I believe this is 1.2 millimeters. On the Techni TEM, I also believe this is about 1.2 millimeters. And specifically, this is referred to as third order because the deviation is proportional to the cube of beta. And that's important to delineate because spherical aberration doesn't stop with just third order. So without going into all the theory, you have higher order spherical aberrations that are odd. Okay, so you have fifth, then you have seventh, and you have ninth. You also have first, but first is actually referred to as defocus, which is something that we can easily correct because we have the ability to tune the focus of the lens. But that is technically first order spherical aberration. Okay, but when we're talking about C sub S, we're referring to usually third order. Okay, so a little bit of a sidetrack here. When we're talking about STEM operating modes, we have two main ways we can do this. So the traditional way was in conventional mode, otherwise known as just TEM mode. That's where you have a fixed or static beam. That beam that is incident on the sample is relatively, I say relatively because it could be just maybe a couple tens of nanometers wide, which obviously doesn't sound very broad, but it's obviously not focused to as small as it could be. Okay, and then there's a bunch of subtypes of TEM, but the most relevant in terms of getting detail is what's called high resolution or lattice imaging. And then the other mode is called STEM mode or scanning TEM mode, where you're scanning a beam and that incident beam is focused on the sample. There are, again, many subtypes of this, but the most relevant subtype is what's called HAADF-STEM imaging, high angle annular dark field. And all of the STEM images I'm going to show you today are of this type. They provide images that are basically chemically sensitive. So they're sensitive to the atomic number of the atoms that are present. They do not actually tell you directly what atoms you have present. We have to do that analytically, which I will go over as well. So when you see the term S/TEM, what that means is that you have a tool that can operate as a TEM or a STEM. So if you look on our website, you'll see for our three instruments, we have the Techni and it's listed as an STEM, the Talos is listed as an STEM, and the Themis is also listed as an STEM because they can all operate in both TEM or STEM modes. So if we want to compare TEM versus STEM, we can dissect the microscope into basically two main regimes. So basically, if this is the sample right here, we can talk about what happens before or above the specimen and what happens underneath it. So basically, above it, we call that the illumination system, and below it, we call that the imaging system. So there's a bunch of lenses involved with the illumination system, as well as the imaging system. But again, what matters ultimately is the objective lens. So the objective lens in an STEM is rather unique in that it's an immersion lens. So what that means is that in principle, it actually functions like two objective lenses, which we call a pre-field and a post-field. Okay, so keep that in mind here. So if we want to delineate now what happens in TEM versus STEM, this is what happens in TEM mode. So you have your electrons coming through and they're broadly illuminating an area on the sample, again, relatively speaking. Okay, if we talk about what happens in STEM mode, then we get something like this. Okay, you'll notice I didn't draw any more rays underneath here. Okay, the reason for that being that the resolution in STEM mode is basically irrelevant relative to what happens underneath the sample. It's basically only concerning what happens up here. When you're talking about TEM mode, it's the opposite. Okay, in TEM mode, when you're talking about resolution, what happens underneath the sample is what becomes more relevant. Okay. Okay, so if you're talking about TEM mode, the relevant part of the objective lens is the post field. That's important to consider. That's what's going to be limiting your resolution. Whereas in STEM mode, it's the pre-field that you have to be concerned about. Okay, so we have this CS coefficient, C sub S. We have lambda, which of course is the wavelength. So there's actually a couple of very simple equations that are well known for high resolution and STEM imaging resolution. Okay, so for high resolution, we see something like this. We have C sub S, and then we have lambda cubed, all to the 1/4 power with 0.64 in front of it. The equation for STEM looks very similar. The only difference is that the coefficient in front is now 0.43. But aside from that, the equation is very similar. Okay, So we can just take a look at this, and we want to ask ourselves, how do we make that delta term small? Well, there's two ways to do it, right? We make C sub S small, or we make lambda small. Okay, so if we start by addressing the issue of lambda, if we want to make lambda small, all we have to do is increase the beam voltage. That works up to a point. The reason why that doesn't work indefinitely is if you make the voltage too high, you end up causing damage to the specimen. And then that sort of defeats the whole purpose as to why you want to image it. So if we're doing standard kind of physical sciences work, you don't usually see that being done at higher than 300 kilovolts. And again, that is material dependent. Some materials can withstand 300 kilovolts just fine. Some can withstand no higher than 200 kilovolts. There's some that can't withstand 100 kilovolts. It is material dependent. Generally speaking, though, 300 kilovolts is kind of a general cutoff for physical sciences work. Okay, so we can't make lambda as small as we want. So the remaining option then is to work with making C sub S smaller. Okay, so we saw here how we have the pre-field and the post-field of the objective lens. So there's basically two ways we can do CS correction. Okay, we can either correct the pre-field or we can correct the post-field. Okay, so without going into too much detail here, it's more or less unanimous. In fact, I've never heard a dissenting voice on this, although there may be one, but it's basically universally agreed upon that it is far more useful to correct the pre-field than it is to correct the post-field in terms of what you can do with the CS correction. Okay, so the reason for that, of course, is that the STEM imaging, without going into too much detail, provides images that tend to be more useful than you can get in TEM mode, and it also provides advantages in terms of analytical capability that you can't get in TEM mode. Okay, so if we're correcting the pre-field, we call that probe corrected. This is the kind of correction that we have on our Themis. And this is what you're going to see with the rest of the data that's going to be shown in this presentation. Okay, so the question, of course, is how does CS correction work? Okay, let's start by discussing how it doesn't work. It doesn't work by making a perfect lens. Okay, that is currently physically impossible. I say currently because people have throughout history said famous things like we'd never make atomic weapons and we'd never put a man on the moon and so on and so forth, and they were always proven wrong. So I'm not putting it beyond possibility that maybe someday we will come up with the technology to make a perfect objective lens, but currently we can't do this. How it does work, though, is by adding additional hardware to the tool to compensate for C sub S. Okay, this hardware is called correctors, right? Obviously. Okay, so I'm going to use an analogy for this, which is relatable to many of you, and that is glasses or contact lenses. Okay, so glasses kind of function the same way that correctors do, although they don't correct the same defect, but the basic idea is the same. So the glasses analogy, maybe some of you are familiar with this, right? So and in my case, right, I'm this middle eye here. I am nearsighted. My eyes are apparently a little, too long, right? So what happens is when an image comes in, it doesn't get focused on my optic nerve properly, so I end up with a blurry image when I'm trying to watch or look at distances. Okay, if you're farsighted, your eye is not long enough. So the way that this is fixed is with glasses. Okay, so you put an appropriate lens in front of the nearsighted person, and that basically accounts for the focusing effect of your eye being too long. Okay, you can do the same thing if you're farsighted, but you need a different lens. Okay, same thing works with contacts, right? You have to use the right contact lens to correct the problem. Okay. Okay, so you're not making your eye better, right, by doing this, although there are technically, right, you have LASIK surgery and things like that. Okay, but what you're doing is you're adding hardware, aka glasses, to in front of your eyes to correct for the size of your eye. Okay, so that's the analogy here, right? We have an uncorrected scenario here. Then we add in the correctors, and we get this, okay? So again, it's like I put, you know, the appropriate lens, if you will, or they're not technically lenses, they're called correctors, but I put the correctors up there, and then when my electrons go through the corrector, okay, and then they go through the lens, the effect is that I get the rays to focus to the same point. Okay, so those correctors are basically, if I go back here just to, well, actually I can use this slide on the left here. So if I know, for example, that this ray is going to be bent by a certain amount, I can use the corrector to basically compensate for that by pre-deflecting it to account for that. And then I can end up with something like this. Okay, so that's how CS correction works. We have to add hardware to the tool to do it. So if we make C sub S 0, does that mean I get resolution of 0? That would be nice, but no, unfortunately, it doesn't work that way. So remember, there's more than just third order spherical aberration. You have odd power spherical aberrations. Currently, you can get systems that are third and fifth order corrected. The Themis that we have is corrected to third and fifth order. You also have to potentially worry about chromatic aberration, especially when your nominal voltage becomes lower. And this is actually kind of the new focus of aberration correction right now. So even with CS correction, you can't make the resolution as small as you want. There's still a practical limit. But we can look at some of the results of doing this. Okay, so there's kind of two regimes for this. So the first one is imaging. And so what we can get with CS correction for STEM is we can resolve picoscale features over a range of voltages from 30 up to 300 kilovolts. So commercially, we have a tool that can do this. Okay? We have a tool that can get sub 60 picometers at 300 kilovolts and approximately 100 picometers at 30. Okay. The other is analytical. Okay, so analytical, I'll go into this in a little more detail, but this is doing chemical analysis of your specimens. So with CS correction, you not only can form a really small probe, but you can form one with a lot of current in it. This is really beneficial when you're trying to do chemical analysis. And this actually enables faster, I say faster, because technically, when the first atomic resolution chemical analysis was published, it actually was done with a non-corrected tool. And it is possible today as well to do atomic resolution chemical analysis with a non-corrected tool, but it is easier and faster to do it with a corrected tool, okay, using either energy dispersive spectroscopy or electron energy loss spectroscopy. So we're going to start looking at some images here. So one of the archetypical materials that is studied with HAADF-STEM for a long time and is still studied is strontium titanate. Okay, which is a perovskite structure. So I already showed you this image, right? That's the uncorrected, that's the corrected, okay? And what you're seeing here is an overlay graphic that's basically a projection of the structure that we would be seeing if we looked along the 001 zone axis, okay? So those bright dots you're seeing, those would be the strontium. Those second brightest dots, those are actually those are the titanium and oxygen columns. And then there are oxygen-only columns that get kind of swamped out because they are lower Z. Okay, so again, my analogy here, it's like switching from standard to high definition TV, right? It's very, very dramatic. Okay, and so if we talk about pushing the resolution at 200 kilovolts, okay, so this is germanium viewed along the 211 zone axis at 200 kilovolts. Okay, this is 87 picometers separation. We can see the separation between those pairs of germanium atoms, which we call the dumbbells. Okay, the projection of the structure looks like that. Okay, so we're resolving sub-angstrom features here. And then this is what we have on our tool at 300 kilovolts, is if we look at gallium nitride along the 211 or the 101 bar 1, I apologize, that bar should be over the third index, not the 0. Not sure why that's showing. But you can actually see, again, pairs of dots, and those are actually pairs of germanium atoms. And those are separated by 63 picometers. Okay, if we look at the projection of the structure, that's what it looks like. So there are nitrogen atoms in the structure. They're actually swamped out because the germanium or the gallium is just much higher Z than the nitrogen. Okay, but those pairs of green dots, right, those overlay with the gallium. And those are separated by 63 picometers. This is the resolution test that we actually use on our Themis. Okay, and this is continually being broken. This happens every couple years where a company comes out and they say we've broken the STEM resolution record, and we've surpassed some sort of barrier. Okay, so that's what's done at higher voltages, but you also have a really big advantage at lower kV. So getting atomic resolution at higher kilovolts in STEM mode was always possible, but it was really basically not possible to do at lower kilovolts until we had CS correction. So if we look at silicon, for example, viewed along a 110 zone axis at 60 kilovolts, okay, we can clearly see the pairs of silicon atoms, or columns of silicon atoms, I should say. Those are separated by 163 picometers. Okay, so this is actually, even though the separation is 163 picometers, we can actually deduce that the detail in this picture is actually sub 100 picometers based on that lower right inset, which is called the fast Fourier transform, which I'm not going to get into in extreme detail, but we can actually use that to figure out the detail limit of the image. Okay, another example, and that's the projection, of course. You have the pairs of atoms which correspond to those blue dots. Another example is molybdenum disulfide. So I don't have a projection for this one because molybdenum disulfide is, of course, a monolayer material, and this is a multi-layer structure. So using a projection doesn't necessarily make a lot of sense here. But what you can see, the separation here, this is about the same as what you see in the silicon. This is at 30 kilovolts. Okay, and again, if you look at the FFT, you again see detail that is close to 100 picometers at 30 kilovolts. Okay, so the CS correction not only works well at high kilovolts, but it also enables, finally, lower kV atomic resolution imaging. All right, so the other advantage that I mentioned was that you can get small probes with a lot of current. Okay, so we're going to look again at silicon along the 110 zone axis. This is 200 kilovolts. So going from left to right, you're starting with 16 picoamps, and on the right, you're getting close to a nanoamp. Okay, so you're talking about orders of magnitude current from left to right, but if you compute the FFT of each of these images, you actually are able to see sub-angstrom detail in each of these images, up to a nanoamp of current. Okay, again, that's the projection of the structure, right? That's the projection of the structure. Okay, now you can clearly see that on the left, where my current is lower, that my separation between the atoms is clearly better. Okay, so the detail in the image is clearly better at lower current, but I can still get really, really detailed images even at a very high current. A nanoamp of current is very high in terms of a STEM probe. Okay, so we still have this classic current resolution trade-off, which anybody who does STEM or even SCM is aware of, but we can still get 100 picometer detail up to a nanoamp. Okay, if we were to compare that, for example, with an uncorrected STEM at 200 kilovolts, you'd probably end up with something that's about a nanometer in terms of the probe. So you're talking about basically a factor of 10 difference in terms of the probe size for the same current. All right, so switching regimes here a little bit to what's called analytical STEM. So if I take my probe and I hit my specimen, I have a STEM detector. I can actually use this to gain chemical information about my specimen, and that's called analytical microscopy, analytical electron microscopy. There's two flavors of this. So the first one is called EDS, which I'm sure many of you are familiar with, where we strike the sample, we generate characteristic X-rays, those are detected. We can measure the X-ray energy, and we end up with an EDS spectrum like what you're seeing here, where we have counts versus X-ray energy, and we can use the X-ray energy to figure out what elements we have present in the sample. The other way we can do analytical STEM is by examining the electrons themselves that transmit through the sample. Okay, we use what's called an imaging filter or a spectrometer, and we can measure the electrons in terms of their energy loss. And again, we see characteristic peaks in the spectrum, and that can be used to determine chemical information. Similarly to what we see with EDS, but we do get some additional information in EELS that we don't get in EDS, which we'll go into in more detail here shortly. Okay, so for now, we're going to concentrate on the left here, which is the EDS side of this. Okay, so atomic resolution imaging, EDS mapping. Okay, so I mentioned before in that image of the strontium titanate, we had the columns of the different atoms. But again, those were images, okay? The images are chemically sensitive, but they don't actually tell you what elements you have present. Okay, in order to do that analytically, you'd have to do EDS or you'd have to do EELS. So you can actually do this analytically at an atomic level with a CS corrected tool. Okay, so you can collect the characteristic X-rays for titanium, strontium, oxygen. You can then map those, right? Like you see here, and then you can overlay them. Okay, and so you actually see a map that looks very similar to the STEM image. Okay, again, that's what the projection looks like you're seeing right there. Okay, so again, atomic resolution EDS mapping. Here's another example of this. So this is a different material. This is gallium arsenide. Gallium arsenide is interesting because the gallium and the arsenic, they're not very different in the Z. So if you look at the STEM image, you're not going to see a lot of contrast. Like in contrast here, you see the difference here between the strontium and the titanium oxygen columns very clearly, but you really don't see that here in the STEM image of the gallium arsenide. But you can analytically figure out which columns are which. Okay, so again, you can map the gallium and you can map the arsenic X-rays. You can do an overlay, and you can clearly see I have columns of arsenic versus columns of gallium. And here's just another example of this, of atomic resolution EDS mapping. The main reason I want to put this in here, we see two maps here that clearly show atomic resolution EDS across an oxide interface. Okay, but what you can see, very interesting here, is that in the left, I see better detail than I do on the right. The difference between these samples is thickness. Okay, so you can see here, right, one of the overarching rules of TEM, right, is thinner samples are better, right? So you can see clearly I have an advantage of the thinner sample that I have with the thicker sample. Okay, so sample prep is still an important role even with CS correction. Okay, but even in a thicker sample, you can still get atomic resolution EDS mapping. Okay, and then how sensitive can we get? We can actually detect a single atom, okay, with a good enough system. Okay, so when I say a good enough system, that means that you have a small probe with a high current, but you also have a really good EDS system, meaning one with a high solid angle of collection. We have one of these on our Themis. It's called a Super X system, and it has a very high, relatively speaking, solid angle of collection on it. So the image you're seeing here, this bright spot here is a single atom, and it's on a monolayer of graphene. Well, the question, of course, is what's the atom? Okay, you can actually analytically, by mapping the signal across here, you can figure out what this atom is. Okay, and you find out this is actually, you find out this is a silicon atom. Okay, and you have analytical proof. So what they did was they actually added up all the spectra around this atom, and they see a silicon peak here. Okay, so they said that's got to be a silicon atom. This copper, that's from the grid, just FYI. The carbon, obviously, that's from the underlying monolayer of graphene. And then, so moving on to the other half of this, which is the EELS, we can do something similar to what we did with the EDS mapping, and that we can do atomic mapping. But instead of using EDS, we're using EELS. Okay, so we have another perovskite structure here, which is barium strontium titanate. This is actually some interface right here. Okay, again, you can see the STEM image. You can see clearly I have some darker features and some lighter features. But then I can map barium, strontium, and titanium here, make a nice overlay like this, and I can clearly see that interface between the two. Okay. Again, that's the projection of the structure. The L23, those refer to core loss edges in the EELS, which we don't need to get into in more detail. Those are very much analogous, like when you see peaks in the EDS. Okay, how sensitive can we be with EELS? We can, again, single atom detect using EELS. So this was some really interesting work out of the STEM group at Oak Ridge National Labs, where they were actually able to analytically prove that in this column of atoms right here, okay, they were actually able to analytically prove by looking at the EELS spectra. So you can see here, here's the different EELS spectra for lanthanum in the vicinity of what's called the M45 edge, which is a characteristic EELS edge for lanthanum. You can see, right, because this line here corresponds to right over this atom column, I have these two peaks, okay, that I don't have anywhere else. So they were actually able to analytically show that they've got single dopant atoms inside one of these columns, okay, lanthanum inside calcium titanate. In principle, right, you could have more than one, although statistically speaking, it's not very likely. But this is kind of the limit, right, of what you can do with EELS. You can detect single atoms. So the other thing that EELS gives you that you don't get with EDS is oxidation state or fine structure analysis. So if you want to learn, for example, if your atoms are, say, doubly ionized or triply ionized, you can't do that with EDS, but you can do it with EELS. So you can actually, in this case, this is cerium oxide, and this is a cerium oxide nanoparticle, and you can actually look at the EELS spectra as you move from the middle of the particle toward the edge. And so you see the different cerium, I should say, as you move, in this case, from H to A. So you can actually see how this changes as you get closer to the surface. And what that actually is indicative of is a change in the oxidation state of the cerium as you move from the bulk basically toward the edge. Okay, so how detailed can you do this? So what they did here was they actually mapped the oxidation state around the edge of a cerium particle. So the red corresponds to one oxidation state, the green corresponds to another. And you can actually see that you have a preference for one oxidation state on the edges of the particle, on the surface, if you will. And you can actually do this at an atomic level even. Okay, so you can see clearly, right, I'm doing atomic level resolution. I can see the change in the oxidation state as I go from the bulk out to the surface. Okay, so CS correction is what enables this by and large. So not only can we do atomic level element mapping, we can actually do atomic level oxidation state mapping as well. So are there any drawbacks? We're wrapping up here. So are there any drawbacks of CS correction? Absolutely. Okay, the first one is money. Okay, so you have to shell out a lot of money just for the instrument itself. Although to be sure, the cost of buying a CS corrected tool has dropped very precipitously over the last several years. Okay, because it's just become such a more widespread technology and more people are getting into the game. Okay, so you have the cost of the instrument itself compared to a non-corrected tool is probably going to set you back at least twice as much. But you not only have the cost of the tool, you have the infrastructure for the tool. So if you want a tool that's going to resolve 60 picometer features, you have to house it in an appropriate environment for that. And the room for that is a very expensive room. It has to have certain limits in terms of its electromagnetic interference and its airflow and all these other things. So it's not only the tool, it's the infrastructure for the tool. And then there are maintenance costs. You have to buy a service contract on the tool, and a service contract on a state-of-the-art CS-corrected STEM, as you can imagine, is going to be very expensive. Specimen quality requirements. These become more critical with a CS-corrected instrument. Okay, so having a thin sample, we saw the example I showed you previously, where having the thinner sample gave you the better results. That's obviously true if you have a thinner, or if you have a non-corrected or a corrected tool, but it becomes more critical with a corrected tool. Okay, even to the point where now there are companies that make tools specifically to make better samples, right? So you might have to spend additional money if you want to get specimens that are sufficient quality to get the top performance out of your CS corrected instrument. Ease of use. Having spent many hours with a CS corrected STEM, I can tell you from experience, they are more challenging to operate. As a general rule, anytime you make any system more challenging or you increase its performance, it's going to be more challenging to operate. So there is that to consider as well. Another issue too is that when you're forming these really small probes, and especially if you're making the current really high, you have the potential for beam damage that you probably didn't have with a non-corrected tool, because you're putting a lot of current into a really small area, especially if you're doing this at higher voltages. Okay, and I've actually seen this happen with the CS corrected tools where literally you're have the beam on the sample and you just literally eat a hole right through it because your current density is just so high. So summarizing CS corrected STEM, it has enabled picoscale resolution and enabled analytical work at the atomic scale. And in terms of the future of this, people are always trying to one-up things, right? So we've got fifth order correction. How high can we go, right? Not only that, but how do we address chromatic aberration? There's a lot of work now in developing hardware for that. There is another way to deal with chromatic aberration, which is with what's called monochromation, which is where you filter the electrons before they get to the specimen. We do have this capability on our instrument. Again, the issue of chromatic aberration, though, becomes more relevant at the lower voltages. Okay, so with that, thank you for your attention. I'd be happy to answer any of your questions.